You know what's really crazy? Every single time you use the GPS on your phone to find the nearest coffee shop or navigate through traffic, you're actually using Einstein's theory of relativity. Not in some abstract way, not in some philosophical sense, but in a very real, very practical, very measurable way. And if we didn't account for time dilation, if we didn't correct for the fact that time runs differently for satellites up in orbit than it does for you standing on the ground, your GPS would be off by miles, not inches, not feet, miles, within just a few hours of operation. Now let me explain something right off the bat. When people hear time travel, they think of science fiction. They think of H.G. Wells and the time machine. They think of going back to meet dinosaurs or jumping forward to see flying cars. But that's not what I'm talking about here. I'm talking about something much more subtle and much more real. Time itself, the thing you think is absolute, the thing you think ticks away the same for everybody everywhere, it doesn't. Time is flexible. Time is relative. And the GPS satellites orbiting above your head right now are living in a slightly different time frame than you are. Let me start with how GPS actually works, because you can't appreciate the relativity part until you understand the basic machinery. You've got about 30 satellites up there, orbiting the Earth at about 12,000 miles above the surface. Each one of those satellites has an atomic clock on board, an incredibly precise clock that keeps time to within nanoseconds. A nanosecond is a billionth of a second. That's how accurate these things are. Now here's what happens when you turn on your GPS. Your phone listens to signals from at least 4 of these satellites. Each satellite is constantly broadcasting a message that says, here's who I am, here's where I am, and here's exactly what time it is right now according to my atomic clock. Your phone receives these signals, and because radio waves travel at the speed of light, which is about 186,000 miles per second, your phone can calculate how far away each satellite is by measuring how long the signal took to arrive. It's like timing an echo. So if the satellite says it sent the signal at exactly 12 o'clock and 15 seconds, and your phone receives it at 12 o'clock and 15.067 seconds, your phone knows that signal traveled for 0.067 seconds. Multiply that by the speed of light, and boom, you know your distance from that satellite. Do this with 4 satellites, and you can triangulate your exact position on Earth. 3 dimensions of space plus 1 dimension of time. That's why you need 4 satellites, not 3. But here's where it gets interesting. Here's where Einstein walks into the room. Those atomic clocks on the satellites, they're not ticking at the same rate as the atomic clocks on the ground. They're running faster. And it's not because there's something wrong with them. It's because time itself is running differently up there. Now, why would that be? Well, Einstein gave us 2 reasons, and they both come from relativity. The first reason comes from special relativity. That's the one where Einstein said, time slows down when you're moving fast. The satellites are moving. They're zipping around the Earth at about 8,000 miles per hour. That's fast by everyday standards, but it's nowhere near the speed of light. Still, it's fast enough that time dilation kicks in. Because the satellites are moving relative to us on the ground, their clocks should run slower than ours. It's a tiny effect, but it's measurable. The satellites lose about 7 microseconds per day compared to clocks on Earth because of their motion. But wait, there's a second effect, and this one goes the other way. This one comes from general relativity, Einstein's theory of gravity. General relativity tells us that gravity isn't just a force pulling things together. Gravity is the warping of space-time itself. The stronger the gravitational field you're in, the slower time runs. Down here on the surface of the Earth, we're deep in Earth's gravitational well. The satellites up there at 12,000 miles, they're in a weaker gravitational field, so their clocks should run faster than ours. Now let me give you the numbers, because this is where it gets wild. Special relativity says the satellite clocks lose about 7 microseconds per day. General relativity says the satellite clocks gain about 45 microseconds per day. You add those together, or actually you subtract them because they go in opposite directions, and you get a net gain of about 38 microseconds per day for the satellite clocks compared to the ground clocks. 38 microseconds. That doesn't sound like much, does it? A microsecond is a millionth of a second. But remember, GPS works by timing signals that travel at the speed of light. Light travels about 1 foot in a nanosecond. So if your timing is off by 38 microseconds, that's 38,000 nanoseconds. That's an error of about 38,000 feet. That's over 7 miles. In one day, your GPS would drift by 7 miles if we didn't correct for relativity. So what do the engineers do? They program the satellite clocks to tick at a slightly different rate before they even launch them into space. The satellite clocks are deliberately set to run slow so that once they get up into orbit and relativity kicks in, they'll be ticking at exactly the same rate as clocks on the ground. It's a relativistic correction built right into the hardware. Now think about what this means. Every time you use GPS, you're using Einstein's equations. You're using the fact that time is relative. You're using the fact that time runs differently in different gravitational fields and at different speeds. This isn't philosophy. This isn't abstract mathematics. This is engineering. This is technology. This is proof that relativity is real. And here's the kicker. The people who built the first GPS satellites, some of them didn't believe this would matter. Some of the engineers thought, relativity, that's just theory. It's too small to matter. We don't need to worry about it. And guess what? The first time they turned on the system, it didn't work right. The positions were drifting. They had to go back and put in the relativistic corrections, and then it worked perfectly. So when I say your GPS proves time travel is real, this is what I mean. The satellites are traveling through time at a different rate than you are. It's not dramatic. It's not like they're jumping years into the future, but they are experiencing time differently. If you could somehow synchronize a clock on a satellite with a clock on the ground, and then wait a while and bring them back together, they would disagree about how much time had passed. The satellite clock would be ahead by those 38 microseconds per day. Now let me dig a little deeper into the physics here, because I want you to really understand what's going on. Special relativity, the part about motion, comes from Einstein's insight that the speed of light is always the same no matter how fast you're moving. That's the key. If you're standing still and you measure the speed of a light beam, you get 186,000 miles per second. If you're on a rocket ship going half the speed of light and you measure the speed of a light beam, you still get 186,000 miles per second. Not 186,000 plus your speed or minus your speed, just 186,000, always. Now that sounds innocent, but it leads to something wild. If the speed of light is the same for everybody, then time and space have to be flexible. They have to stretch and squash to make the math work out. When you're moving fast, your clock runs slow compared to someone who's standing still. It's not an illusion. It's not a trick. Your clock really does tick slower. Time itself is running slower for you. The formula is actually pretty simple. If you're moving at some velocity v, and c is the speed of light, then your time is slowed down by a factor of the square root of 1 minus v squared over c squared. For everyday speeds, v is so much smaller than c that this factor is almost exactly 1. But when v starts to get big, when you're moving at a significant fraction of the speed of light, that factor gets noticeably smaller than 1, and time slows down a lot. For the GPS satellites moving at 8,000 miles per hour, v over c is tiny, but it's not zero. It's enough to cause that 7 microsecond per day slowdown. You plug in the numbers, you do the math, and out comes 7 microseconds. It's not a guess. It's not a fudge factor. It's a prediction from Einstein's equations, and it's exactly what we measure. Now, general relativity, the gravity part, that's even more beautiful. Einstein figured out that gravity isn't a force at all. It's the shape of spacetime. Imagine spacetime as a rubber sheet. If you put a heavy ball on the sheet, it makes a dent. That dent is what we call gravity. Objects roll toward the ball, not because the ball is pulling them, but because they're following the curved shape of the sheet. And here's the thing. Time runs slower in that dent. The closer you are to a massive object, the slower your clock ticks. It's as if time itself is being stretched by the gravitational field. Down here on Earth's surface, we're in a stronger gravitational field than the satellites are, so our clocks run slower than theirs. The satellites, sitting up there in a weaker field, their clocks tick faster. The formula for this comes from the Schwarzschild solution to Einstein's field equations. The time dilation factor depends on the gravitational potential, which depends on how far you are from the center of the Earth. The satellites are about 4,000 miles farther from the center than we are, so they're in a weaker potential, and their clocks run faster by about 45 microseconds per day. Again, you plug in the numbers, you do the math, and out it comes. 45 microseconds, not 44, not 46, 45. And when you combine this with the special relativity effect going the other way, you get net 38 microseconds, and that's exactly what the GPS engineers have to correct for. Now let me tell you why I think this is so amazing. It's not just that relativity is real, it's that it's so precise. Einstein didn't have GPS satellites, he didn't have atomic clocks. He was working with pure thought, pure mathematics, pure logic. He was sitting in a patent office in Switzerland in 1905 thinking about trains and clocks and light beams, and he figured out that time is relative. Then in 1915, he extended it to gravity, and he figured out that gravity warps space-time. And now, 100 years later, we've built a technology that depends completely on those insights. We've put atomic clocks in orbit, we've measured time dilation down to the nanosecond, and it all works exactly the way Einstein said it would. That's the power of physics. That's the power of mathematics. You sit down with a pencil and paper, you work out the equations, you make a prediction, and then a century later, somebody builds a machine that proves you were right. But here's the deeper question. What does this mean for time travel? I mean real-time travel, not just satellites ticking faster. Well, the truth is, we already know how to travel into the future. You just have to move fast or stay in a weak gravitational field. If you got on a rocket ship and accelerated to 99% of the speed of light and flew around for what felt like 1 year to you, then came back to Earth, you'd find that decades had passed here. You would have traveled into the future. That's not science fiction, that's just relativity. The problem is it's hard. Accelerating to 99% of the speed of light takes an enormous amount of energy. We don't have rockets that can do that. But in principle, it's possible. In fact, it's inevitable. If you move fast enough, you will travel into the future. Going backward in time, that's a different story. That's much harder. General relativity does have solutions that allow for closed time-like curves, which is the fancy physics term for time travel into the past. But all of those solutions require exotic things like rotating black holes or wormholes or negative energy, and we don't know if any of that is really possible. The universe might have some kind of protection mechanism that prevents backward time travel. We call it the chronology protection conjecture, but nobody knows for sure. What we do know is that time is not absolute. It's not the same for everybody. It depends on how you're moving and where you are in a gravitational field, and that's profoundly weird if you stop and think about it. Your intuition, built from everyday experience, tells you that time is the same everywhere. 1 second for you is 1 second for me, is 1 second for a satellite is 1 second for an astronaut. But that's wrong. That's just an approximation that works at low speeds and weak gravity. When you look closely, when you build precise clocks and put them in different places, the illusion falls apart. And the GPS satellites are the perfect demonstration of this because they're so practical, so mundane, so everyday. You're not looking at some exotic particle accelerator experiment. You're not waiting for a gravitational wave detector to pick up a signal from colliding black holes. You're just pulling out your phone to find the nearest pizza place, and boom, there's relativity working in the background, making sure you don't end up 7 miles away. So the next time you use your GPS, I want you to think about this. Think about the fact that the satellites above you are living in a slightly different time frame. They're experiencing time at a different rate. They're proof that time travel, at least in the sense of differential aging, is absolutely real. It's not some wild speculation. It's not some fringe theory. It's built into the technology you use every day. And if that doesn't make you stop and wonder about the nature of reality, I don't know what will. Einstein once said that the most incomprehensible thing about the universe is that it's comprehensible. We can understand it. We can write down equations that describe it. We can make predictions and test them and build machines that work because our predictions were right. That's astonishing. That's beautiful. And that's what physics is all about.